corner principle was easy to apply in our example, but that's not always the case. It's conceivable you could have a weirdly shaped feasible region and therefore a lot of corners to deal with. And a lot of corners means a lot of computation. Not difficult in theory, but it can mean substantial difficulty with the method in practice. There's another difficulty, something a little more exotic. In our example, the feasible region was two-dimensional, easy to visualize and easy to graph. But it can happen that the problem requires 3 dimensions, or even more. If it's more than 3, you can't even visualize what the feasible region might look like. How can you tackle a problem like that? You'll be glad to know that there is a method for this situation, a linear programming technique called the simplex method. The problem of visualizing higher dimensions just disappears because the simplex method is completely algebraic. No need for a geometric picture. But just to get the idea, imagine a feasible region that's a polyhedron with many corners. The first step in the simplex method is like the beginning of a card trick. Pick a corner, any corner. It really doesn't matter where you start, because the simplex method is a procedure for getting from one corner to a neighboring corner whose value is closer to the optimal solution. By neighbor, I mean a corner that you can get to from the corner you're on by walking along an edge of this polyhedron. The yellow corner and our original corner are neighbors. The red one is not, because even though it seems closer, we can't get there by walking along just one edge. From any one corner, like the one we chose, the algebra of the simplex method allows you to compute from the corner you're already on which neighbor you should try next, which one moves you in the right direction, so to speak. In our example, the computations would lead from our original corner to this neighbor, then from there to a neighbor of that corner, and so on, until you reach the point that's marked as optimal. So there are a lot of corners you never have to bother to visit, and therefore a lot of calculations you don't have to perform. When the simplex method is used, it visits a very small fraction of the corners, and so it's usually a very efficient way of solving linear programming problems. But mathematicians are never content to assume that just because a method works very well, it's the last word on how to tackle a problem. Very recently, in fact, after years of research, there's been a mathematical development which may improve the efficiency of linear programming. Narendra Karmakar, a young mathematician at Bell Labs, has devised a new procedure for handling very complex linear programming problems. If you imagine the polyhedron we looked at earlier, Dr. Karmakar's method is to start in the center rather than some outside corner. Each time a point is chosen closer to the optimum point, the axes of the polyhedron are stretched in such a way that our new point is now in the center. Theoretically, this process allows you to locate the optimal point with fewer calculations.
As the problems become large and complex, the simplex algorithm takes much longer to solve these, as opposed to the new method, which will be able to handle even larger problems. There are some users who have already started using it, such as internally within AT&T. But then many people have to be trained to understand and use the new methods, and therefore it will take quite some years before it comes into full-fledged application.
Bell Labs supports a lot of pure mathematical research, and that's Dr. Karmakar's field. But the potential applications of his method are very important to many large businesses, including AT&T. Routing millions of long-distance phone calls is a resource allocation problem. How to use long-distance landlines, repeater amplifiers, and satellite terminals to the best possible advantage. Flight crew schedules and aircraft fuel loads are other examples of resource allocation problems. American Airlines is one of the companies interested in Dr. Karmakar's technique to see whether it can help cut costs. Thomas Cook is Director of Operations for American.
If indeed we can get an algorithm that is 50 to 100 times faster than existing technology, we can do a lot of things with that algorithm that we couldn't do today. A good example of that kind of an application is what we call a major weather disruption. If we get a major weather disruption at one of our hubs, like Dallas or Chicago, and a lot of flights get canceled, and we have a lot of crews, a lot of airplanes in the wrong places. And what we need is a way of putting that whole thing back together again so that the crews are in the right place, the airplanes are in the right places, and we minimize the cost of that disruption and minimize the passenger inconvenience of that disruption. Well, we're working on that problem today But in order to solve that problem in an optimal fashion, we need something as fast as Karl-Markow's algorithm to do it. So in the absence of Karl-Markow's algorithm, we'll have to come up with some heuristic kinds of ways of solving that problem that won't be optimal.